Today we're going to look at multiplying probabilities. So we want you to be able to solve problems involving compound independent and compound dependent events. All right, so independent events. We're going to be looking at what happens when you are doing something that is referred to as a compound event. So that's events made up of two or more that happen at the same time or one after another. So when you do a combined independent event, so if you got two events A and B that are independent, that means they have no effect on one another. And how you figure out the probability is to multiply the probability of A happening times the probability of B happening. So when you're dealing with multiple events or events one after another, you multiply the probabilities together. So let's look at an example. Number one here says Julio reaches into an ice-filled cooler containing 8 regular soft drinks and 5 diet soft drinks. He removes a can, then decides he's not really thirsty and puts it back. What's the probability that Julio and the next person to reach in the cooler both randomly select a regular soft drink? Well, from what we talked about probability before, you're looking for what makes this successful. In this case, a regular soft drink, which we know there's 8 of. So we got 8. And then on the bottom, we need our total. And the total here would be 8 plus 5, which is 13. So our total is 13. So that would be the probability that Julio reached in and got a regular soft drink. Now that he's putting it back, though, the next person should have the exact same probability of also selecting a regular soda of 8 out of 13. So the probability that they both select would be whatever we get when we multiply these two together. Well, remember when you're multiplying fractions, you multiply the numerators. So 8 times 8 is 64. You multiply the denominators across. 13 times 13 is 169. And then that becomes your probability. So the probability would be 64 out of 169. You could also list this off as a fraction if you wanted, because if you have 64 out of 169, that's kind of hard to think about how likely is that to happen. So if you went on your calculator and put this in, 64 divided by 169, we could change this to a decimal, so it would be about that probability. If you multiply by 100, now it's a percentage, so it's about 37.9% chance, about 37.9% chance of happening. That's a little bit easier to maybe comprehend about how likely that is going to be. Okay, let's try another one. It says in a state lottery game, each of 3 cages contains 10 balls. The balls are each labeled with one of the digits 0 through 9. What's the probability the first 2 balls will be even and the third will be prime? Well, if the balls are 0 through 9, if we include 0, that's 10 possibilities. And so we got 10 different choices, so our total each time is going to be 10. We want to look at what makes these true. Even numbers, we got 0, 2, 4, 6, 8, and I guess we're not including 10 here. So it looks like there's 5 things that make that true. Prime numbers, if you recall, are numbers that are only divisible by itself and 1. And 1 itself is not prime because 1 we consider the number of origins. So we got 2 would be prime. It's the only even prime number. 3 would be prime. 4 is not prime because 4 can be divided by 2. 5 is prime. 6 is not prime because it's divisible by 2 and 3. 7 is prime. And 8 and 9 would not be prime because they're both divisible by either 2 or 3. So there's 4 prime numbers. Okay, so now let's figure out our probability here. What's the probability that the first ball will be even? Well, there's 5 things that make that true out of 10 possibilities. The second one even would be the same probability as 5 out of 10. And the third cage, we got 4 prime out of 10. And so to figure out the probability of all 3 things happening, we multiply that together. So if you multiply everything on the top, that's 100. You multiply everything on the bottom, that's 1,000. And so the probability here, we could simplify that. That would be the same as 1 out of 10, or that's the same as 10% chance. So either one of these two answers would be good. Okay, so that's what's called compound independent events. So looking how this works here, compound events, that's when more than one thing is happening, more than one event. We looked at independent events. That's the ones we just did. That's where the outcome does not influence the second event. The other thing that could happen, though, is what's called a dependent event. And that's when the outcome does affect or influence the outcome of the second or third or fourth event, and so on. So when your choices after your first one get affected, we call that dependent. Let's look at some of those types of problems. So in example 3, they want us to figure out for each of these, is it independent or is it dependent? So if you toss a coin and roll a die would be like a single dice. Do those things have any bearing on each other? Would tossing the coin affect what you get when you roll a dice? Well, in this case, no, those don't have anything to do with each other, so we would say that this is an independent event. One doesn't have anything to do with the other. In B, it says selecting a red apple, then a green apple from a bag that contains 6 red and 4 green apples, if no apples are returned to the bag after being selected. Okay, well, if you're taking one apple out, then your choice for the next apple is affected because the total is not the same anymore. So we would say this is a dependent event. When you take something out and do not return it, then the next probability is going to be different. If we read through C, it's the same problem, except that after the first selection, the apple's returned to the bag before the next is selected. Well, if you return it, the second person now has the same chances of doing whatever you're doing for the second one. This would now be independent. So when you replace, we call it with replacement, then it becomes independent. If it's without replacing it, then you say it's dependent. Okay, so we kind of know the difference now. Let's try some of these dependent problems out. So the probability of a dependent one is the probability that the first thing occurs, and then the probability of something else happening after. So you're going to have to change it, but we still multiply them together. We're still going to be multiplying when we do these problems. So for number 4, it says find the probability of drawing 3 cards of the same suit from a standard deck of cards. And recall, members, deck of cards, we know there's 52 total, without, this is important, replacement. So if we're doing without replacement, that's telling us this is going to be a dependent problem. So first, we got to figure out what's the probability of drawing 3 cards of the same suit without replacing them. Well, did they, in this problem, they never told us what this suit is. It could be any of the 4 suits. So our first choice really can be any card. We don't really care what the first card is. So our probability of drawing the first card would be 52 out of 52. We don't know what it's going to be, and we don't care. Okay, now let's say it comes out to be, we just pick one and it's a club. Okay, well now we're focusing in on clubs for the next choice here. So how many cards are going to be left out of the deck? Well, we picked one out, so now it's down to 51 cards. And assuming we drew, like, let's say, a club, the rest of them have to be clubs. How many clubs are going to be left in our deck? Well, we know there's 13 cards of each suit. So assuming we picked one on our first one, that means 13 minus 1 is going to leave 12 left in the deck for our second choice. So now let's assume we picked another club. What's our chance of picking that third one? Well, now we're down to 50 cards in the deck. And if we have one less club in there, that means we're down to 11 clubs. So our probability of getting 3 straight cards of the same suit will be whatever we get when we multiply this together. So again, when you're multiplying fractions, multiply across the top. So let's multiply all those together. So 52 times 12 times 11 is going to give us 6,864. And on the bottom, now we got to multiply those together. 52 times 51 times 50. And we get this. Okay, so now what would the answer be? This is the answer. But again, remember, like on those, what we talked about before on the ACT or something, if this is a multiple choice answer, you're probably not going to see that as one of your choices. You would want to simplify that out. So how you can do that again is if you divide these out on your calculator. This is what it would be as a decimal, or we could easily change that into a percentage. It looks like it's about 5.2%. But if you want to change it to a simplified fraction, hit math and then fraction, and then it'll change this to a simplified fraction. 22 out of 425 would be the same thing, just simplified out. So another way we could write this answer would be 22 out of 425, or that was about 5.2%. So one of those two answers is probably how you'd have to answer it on a test. All right, let's look at some more problems here. So now each of these we got to go through and figure out, is it independent or dependent, and then also figure out what is the probability going to be. So let's take a look at another card problem. It says 3 cards are drawn from a standard deck without replacement. Okay, that's a big key in this one again. It's not being replaced. What's the probability of drawing heart, heart, and spade in that order? Well, if they're not being replaced, these choices are going to be dependent because your total is going to be different each time. So the first heart, our chance would be 13 cards in every suit out of 52. Okay, here wouldn't be any card. We specifically need a heart. Another heart now, okay, so we'd be, if we chose one on the first one, there'd be 12 left in the deck out of 51 cards. And then choosing a spade on the last one, we'd be down to 50 cards in the deck. All the spades are still in there though, so our total for spades would be 13 out of 50. So if you multiply these together now, you should get the probability. So if you multiply everything on top, you get that. If you multiply everything on the bottom, it's the same total as the last problem. Simplified, that's the same as 13 out of 850. Or as a percentage, it'd be about 1.5% chance. Not very likely that that happens. All right, let's try another one here. B, it says, spin a spinner numbered 1 to 7 and toss a coin. What's the probability of getting an odd on the spinner and a tail on a coin? Spinning a spinner and a coin don't have any, don't have anything to do with each other. So this would not be dependent. This would be independent. These are separate things. They don't affect each other. So what's our probability of getting an odd? Well, from 1 to 7, we have, looks like 4 odd numbers. So it'd be 4 out of 7 chance of getting an odd on the spinner, 1 out of 2 chance of getting a tail on the coin. So together that would be 4 out of 14 or a 2 out of 7 chance. Okay, C. You reach into a bag of Scrabble tiles. The bag contains 1 tile with each letter. So that must mean in the alphabet we got 26 letters. There's 26 tiles here. You pull out 1 tile and then another. What's the probability you pull out a vowel and a consonant? Well, vowels we know in the alphabet is A, E, I, O, and U. So that's 5 of the letters are vowels. That means, with a little math here, there's 21 consonants. So let's try to figure out our probability of what this would be. We're pulling out 1 tile and then another. So we can assume here we're not replacing it. This is going to be dependent. So our chance of getting the vowel, 5 out of 26 chance. If that one tile's already out, we're going to be down to 25 tiles, and there'd still be 21 consonant ones in there. If we multiply this together, this would be our probability. If you multiply that on top, it's 105. 26 times 25 is going to be 650, and that simplifies to 21 out of 130, or about 16.2%. All right, why don't you pause the video, try D and E out on your own, see what you get, and then we'll check them. All right, let's see how you did on these last two here. On D, it says it's a standard deck, 52 cards, without replacing it. Okay, that tells us right there, this is going to be dependent. A second card is chosen. What's the probability that the first card is a queen, the second one is a jack? Well, there's 4 queens out of 52. There's also 4 jacks, but now our total would be down to 51 because we're not putting the card back in. Simplified, this should be 4 out of 663, or that's a very slim chance. It's about 0.6% chance of this happening. So that would be the answer for this one. For E, 4 cards are chosen from a deck with replacing them. So now every choice should be independent of the one before it. What's the probability of getting 4 hearts in a row? Well, we know hearts is 13 cards in the deck. So it'd be 13 out of 52 for the first chance. You put it back, you're still going to be out of 52, and there's still 13 in there. So it'd be 13 out of 52 each time. Now, one suggestion on a problem like this, 13 out of 52, if you go on your calculator and put in 13 out of 52 and divide it, it's 25% chance, which is the same as a simplified fraction of 1 out of 4. So you could simplify all these first before finding the probability. This is the same as a 1 out of 4 chance. This would be the same as 1 out of 4 chance. So it'd be 1 out of 4 times 1 out of 4 times 1 out of 4. So if you multiply these together, that's much easier. 1 times 1 times 1 times 1 is going to be 1. 4 times 4 times 4 times 4 is the same as 4 to the 4th power, which, if we go on our calculator here, 4 to the 4th power would be 256. So the answer would be 1 out of 256 chance of that happening. If you wanted to think of that, if you divided that out, it does come out to be only about a 0.4% chance of happening, pretty close to it anyway. So not very likely that that would happen. Okay, you try some of these ones out now on the practice problems and kind of see how you do.